Okay, howdy and welcome back. We're going to move into the primitive types here. So the primitive built-in types, these are going to be the most basic kind of building blocks from which our C++ programs are going to be constructed from. Included within these types that are afforded to us by the barebone language is going to include a Boolean type, bool, a character type, char, an integer type, int, along with other flavors of integer types, but in this course we'll primarily be using int, and then floating point types such as double. We'll see that there are kind of three flavors of floating point types as well. The reason for double is that double is shorthand for double precision floating point number, which is the computer's approximation to the mathematical concept of a real number. We'll see here that that term approximation is key. And when we get into kind of the representation of these different types, we'll really see how how floating point values truly are approximations. The Boolean character and integer types are known as the integral types together. Together, the integral types and floating point types are known as the arithmetic types. And you might be able to infer why that might be. So the integral and floating point types come in different flavors, which essentially gives us, the user, a choice in the amount of storage consumed, which has direct implications on the range of values that we're able to represent, as well as the precision for those values. For this course, you'll be able to essentially write perfectly good programs in C++ using these 5 primitive types. Bool for logical values, char for characters, int for integer values, and double for floating point values. I will get into some of the different flavors of, say, the integer values and the floating point values, but for all intents and purposes, unless there's a reason to use something else for the reasons mentioned on the previous side, you'll be good using those. So I don't expect, and you shouldn't use something like a float. That has a different level of precision. And if you choose that over a double, you may run into some issues when you submit your code to be auto-graded by CodePost or our in-house system. Likewise, the representation, if you're using a smaller int, you might not be able to maintain all of the values that we're testing your program with. So yeah, for this class, I'm expecting that with respect to the primitive types, these should be sufficient unless we specify otherwise. So each of these types is also going to have a characteristic style of a literal. True or false, written out as such, as shown in the blue text here for Boolean values. For character literals, it's going to be a single character enclosed in single quote. If you use double quotes, that's a string, which is going to be different, and you would not be able to essentially assign or initialize a char with double quotes. You'll get a nice, wonderful error message, which will hopefully decompose when I talk about the compilation process. I can illustrate that one so you're aware of it. If we're looking for a literal of an integer value, it's just going to be a sequence of digits. Likewise, for a double value, it's going to be a sequence of digits with a decimal point somewhere in there. From the primitive types, and you don't need to worry about this today, but it kind of shows perhaps where we're going with this, is that from these primitive types, as I call them, these kind of building blocks for more complicated things in our C++ programs, we can actually create what's known as a compound type. So this would include, say, the pointer types. And you'll kind of understand what this little asterisk is, and then what the subscript is for the array types when we get into the declarations a bit later today. A reference, which isn't really a type, but kind of an alias for a variable or that's already kind of out there, or an object residing. Well, we'll get to that in a bit. And then data structures and classes. We can use combinations of these primitive types or even the compound types to kind of create elaborate collections of details or specific abstractions of entities that we'd like to represent in our program. But again, don't worry about these right now. We'll get to them in due time. So I'm going to kind of go through these with some level of depth. This might be intuitive. You might have kind of already be aware of what will be covered here, but nonetheless, I think it'll be good review. And if not, at least the C++ perspective on this, how it's implemented in this language. So let's talk about the Boolean type first. The possible values are going to be simply true and false. This type is going to be primarily used to express the result of logical operations. We'll get into statements and expressions that of this nature in a couple lessons down the road. But right now, just understand that, it stores true or false. This is probably a good way to store, things of that nature. If we were to include, say, the arithmetics or the Boolean variables in arithmetic or logical expressions, what we'll see, and I'll be sure to highlight this in the next lesson when we are talking about expressions in greater detail, but we can't add a true and a false. So what's always going to be done first is these will be converted to integers per se. So true would have the value of 1 when converted to an integer, false to the value of 0. Any sort of operations are then performed on these converted values. And then if we wanted to store that result back in a Boolean variable, essentially what's going to happen is a non-zero value is going to be converted to true, whereas a 0 value would then be converted to false. So getting into characters a little bit here. So char type, it can hold essentially any character of the implementation's character set. And I'll get into that a bit more here in the next slide, I believe. Each character is essentially going to have essentially a constant for some sort of integer value. And that goes back to a couple of videos ago when we were saying how, in binary, it's not like we could stick a ASCII character of A in there. We only have 1s and 2s to work with. So we'll essentially encode a character as some sort of binary value, which when we interpreted it, it would be, we calculate out some sort of integer value, and then we could go ahead and map that value to a character. So with ASCII, you should probably know the, where A starts and where A ends, but essentially with some value, look it up in a table, and then you can see what characters that particular integer corresponds to. These are integral types, so both arithmetic and logical operations can be applied to them. So when we're creating a variable that's going to store a character, it's safe to assume that these char types can essentially store any of the 26 alphabetical characters of English, any of the decimal digits 0 through 9, basic punctuation characters. However, it is not safe to assume that objects of this type could store more than, say, 127 characters when a byte is used to actually store that, and that no more alphabetical characters than that provided by English are guaranteed to be able to be stored. And another thing that you shouldn't assume is that the alphabetical characters are not necessarily contiguous. So in ASCII, they more or less are. So an I and a J is going to be next to one another in terms of their integer encoding. However, there are other character sets. I'm not sure how frequently it would be that you'd encounter something such as EBCDIC today, unless you're on an old IBM mainframe. But the key component here is there are other character sets, and just be kind of conscious about that, and work. Don't make any assumptions into your program that are kind of based off of you're expecting to have, say, 1, and then you deploy somewhere else and it's different. That'd be a hard bug to kind of track down as well. So character literals. A literal is a notation for representing a fixed value. Character literals are also known as character constants. A character literal is, as we mentioned before, simply a character enclosed by single quotes. So notice here we have character literal A, character literal 9, and then this one right here. Question is, what is that? So some characters are going to have names that use backslash as an escape character. This here is essentially a line feed or a return. There's other special characters that use a backslash, such as -T for tab, -0 for the null character. And there's many others. And you can, there's no reason to memorize this. Go ahead and just look them up if you need a particular character, but understand, things such as tabs, spaces, nothingness, they're all going to have some sort of likely specialized encoding. Likewise, I'll go ahead and just point out here, if we wanted to store a single quote, that character, you'd have to go ahead and escape it as such. That's going to be an additional character that would be escaped. So again, all these are really symbolic constants for the integer value of the respective character and the implementation's character set. So the integer types. There are 3 integer types which are essentially going to vary from one another in terms of their size. And the size is going to have direct implications in terms of the range of values that they could store. So there's a short, which is going to be at least less than size than the integer. Then there's going to be a long, which is going to be at least the size of an integer. In most implementations, it will be larger. So again, for all intents and purposes in this class, an int should be sufficient unless we, discuss otherwise. Each integer type is going to come in 3 forms. There's the kind of plain vanilla int or plain vanilla short, plain vanilla long, and essentially these are going to allow you to store both positive and negative numbers within them. Likewise, we could add in this, as we'll see, it's called a non-type specifier, signed prefix to the name of the type, to an integer type, and that's essentially saying that this object will store both, again, positive and negative values. An unsigned int is going to essentially use the representation of the object which was essentially partitioned to allow us to store both positive and negative numbers, and essentially use all of it for positive numbers. Now the integer literals, they get a little more fun because there's a couple more things to them than just the sequence of digits that we talked about before. They're essentially available to us in 4 forms: decimal form, binary form, octal form, and hexadecimal form. A literal string with 0b prefixed is going to be a binary number, so base 2 number. So if I were to write something like int I is equal to OB, this value in base 2 would be stored in the int as, hopefully I calculated this right, 250. And it might be convenient to essentially work in base 2 in some applications. The one that's probably strikes me, as maybe most productive would be, in an architecture class, if you're having to, simulate some, sort of single cycle machine or whatnot, where the instructions are in base 2. So additionally to having base 2 literals, we have the ability to denote a base 8 number. And this is going to be essentially starting that value out with a 0. So here, if we wanted a base 2 number, base 8, we'd say that I is equal to 0. And then we're not going to have anything after it, followed by the octal number that we're interested in. And this would evaluate to the integer value of 66, because essentially that base 8 value is 66 encoded. Now the last one is going to be a hexadecimal base 16 value. To do that, it's going to be a literal prefix with 0x. So we could have something like int of I is going to be equal to, let's go ahead and say 0x42. So right there, we have a hexadecimal literal. That would evaluate to the base 10 value of 34. Hopefully I computed all of those correctly. So there's also a couple of other things that we can tag on to our literals. And this would have implications when we start talking about conversions, both implicit and explicit conversions. So we'll get to this a bit more, but understand that if we just write out, say, a sequence of binary digits, that's literal is essentially going to be an int. You could think about it as being stored in a temporary object. It's an int. If you wanted that to be, say, a long int, so that different flavor of an int, which was one step larger up from an int, you could write 101 followed by the suffix L. And now the temporary object storing this value would be a long. And that's important because if we wanted to do something like long L is equal to some sort of value, it might be productive to go ahead and specify that that is a long, so that we don't lose any precision, if we were actually using a large value that would otherwise exceed that of a temporary integer. In addition to this, there could be times where we're interested in having a temporary that is unsigned. To do that, we could simply write out the value and then suffix it with u. And that's going to be an integer literal. Again, the temporary object, so to speak, of storing it is going to be an unsigned integer object. Okay, the floating point types, moving right around here. So the floating point is going to be the computer's approximation to the mathematical concept of a real number. And the key here is going to be this idea that they are but approximations. And when we actually decompose this format of how they're stored in this normalized exponential form, you'll see how adjacent floating point numbers, there's kind of a little bit of a gap between them. If you think about this further, there are some base 10 numbers that if we were to convert them into base 2 using this representation, we'd have repeating decimal places, etc. And then when we're dealing with approximations and we start doing, different operations, you also see a propagation of error, etc. So, we've got a lot of precision. Mostly, things are pretty, at least for our application, within a reasonable magnitude of error, but it's just if you're doing high performance computing, scientific computing, it's things you have to kind of think about. So just like the integers, there's going to be 3 different types of floating point types, and they're again vary in the size from one another, which has again a direct implication in terms of the range of values that they can store. Float is going to be a single precision floating point number. Double is going to be double precision. Long double is extended precision. And I'll refer you, to the documentations if you'd like to learn about, a bit more detail as to, why these are named as such. But the key thing taking away here is the exact meaning of single, double, and extended precision with respect to the underlying encoding scheme is going to be implementation dependent. So it's not going to be guaranteed that these are using, the IEEE standard, although, I believe in all likelihood, most are today. Floating point literals. So this is more or less very similar to kind of the, caveats with integers. So the default floating point literal type is double. So if you write something like 3.14, the temporary object storing that, it's going to be a double. If you wanted a floating point literal, you'd have to denote after that with an F. And the reason why that might be beneficial in terms of this is, so a double is a lot kind of bigger than a just a plain old float. And if we were to write out some sort of floating point literal, that's a double, and then attempt to assign it to a float, what we're having is a narrowing conversions going on. And we'll get into this in the next lesson. Essentially, we'd have a big kind of thing that we're trying to fit in a smaller thing, and it might not fit. And there could be ramifications for attempting that conversion in that case. Likewise, if you'd like a long double floating point value, and this is kind of going in the other direction where, you might have a literal that couldn't necessarily fit in just the plain out double. So there'd be some truncation there going on. So if we wanted to say that, hey, the literal we have here is indeed meant to be a long double, we just go ahead and prefix that with L to denote that. So that's the end of kind of our brief discussion on the primitive types. We're going to go ahead and move on here momentarily and do a discussion about variables. Moving on from that, we'll talk about declarations and then finish up with initialization and assignment.